two talks. Today on general background on core of an ideal, and on Friday she will focus on the core of monomial ideals. So, Claudia, over to you.
Thank you very much for the invitation. It's a pleasure, and it's a pleasure to talk to you. I'm sorry I'm not there, but at least I can reach you through Zoom. This is a wonderful technology that we are able to give these talks. So, and thank you everybody that came to listen to me. So let me start. First of all, I will take R to be a Noetherian ring. And I an ideal of R. And to I, we can associate an algebra called the Riese algebra of I. So let me write it down. The Riese algebra is the graded ring in component 0, it has R. In component 1, it has IT. In component 2, it has I square, T square, and so on. And we think of it as the ring inside the polynomial ring RT in one variable over the ring R. And so it's nothing else but the algebra. So let me call it, it's called Riese algebra. So the name is Riese algebra in honor of Riese, but introduced it to start the Arthur-Riese theorem. And this is the algebra generated by IT inside the polynomial ring RT. So geometrically, this algebra corresponds to the blow-up of spec R along V of I. So for this reason, is also called the blow-up algebra of I. And there are many reasons to study the Riese algebra. I will just single out some of them. For example, multiplicity theory, or study the asymptotic property of ideals, or study integral dependence and integral closure, or clearly, as the name suggests, blow-up algebra, resolution of singularities. And even if a blow-up is a fundamental operation, an explicit understanding of this process is still mysterious. And in this context, learning and understanding Riese ring is very important. So the first difficult problem that actually one faces is the problem of computing the defining equations of the Riese ring. And what do I mean with the defining equation? Let me actually move it here. This is the first problem one encounters. And this means really to write the Riese ring as a quotient of a polynomial ring over R and write explicitly its defining ideal. And this problem, which is actually very difficult and is still open for very simple classes of ideal, even free generated ideal in a polynomial ring in two variable, has been investigated widely in commutative algebra, in algebraic geometry, and in elimination theory, and even it's even appeared in applied mathematics, most notably in geometric modeling. The reason is that the Riese ring and understanding or solving this problem really has bearing even in finding the defining equation for any variety that has been defined parametrically. This is because the Riese algebra is the bihomogeneous coordinate ring of the graph of the birational map that is given by the generators of I, at least in the case that I is generated by form of the same degree. Now, to describe RIT in terms of generator relations is often useful to know its algebraic properties. For example, to know if the Riese ring is normal or if it's Come-Colli. So the next question I would like to put up is, when is the Riese ring Come-Colli? Or if you want R1, or how do we characterize normality or R1 condition or the S2 condition? The Come-Colliness is important because it gives us actually bounds on the number and degrees of the defining equation of the Riese ring. Now, if we start from the simple ideal, which is just a complete intersection So assume that I is a complete intersection. And from now on, I will always denote complete intersection just CI when the Riese ring is very well understood. So I'll just put a check mark. In this case, the Riese ring is, come Coli, and is just, the defining equation are just given by the 2x2 minors of a suitable matrix. Let me, in case students don't know, tell you what is a complete intersection. A complete intersection is just an ideal generated by a regular sequence. Or if you think geometrically, means that the variety defined by IV of I is defined by the smallest, is cut out by the smallest number of equations possible. Okay, so the complete intersection are the best kind of ideals. And suppose though, so what is the idea if I is not a complete intersection? So otherwise, one approach to study Riese algebra is to look at or to find a complete intersection inside I, and that is close enough to I. Why do I say that? Because if I have a complete intersection J, the Riese algebra of J will be nice. We'll know exactly what it is and how it looks like. And if the ideal J is close enough to I, then we can hope to transfer the property of the Riese algebra of J to the Riese algebra of I. So to transfer it over. And so this is not always possible, but in general, what we could do, we can define the following important definition for this talk, which is the definition of reduction. So we take J containing I is a reduction. It's called a reduction of I, or you can also say that I is integral over J. If and only if, and this is where my definition comes, I to the n plus 1 is equal J to the I to times I to the n for some n bigger than equal than 0, and actually for every n large enough. So asymptotically, this has to hold. And this is the same as saying that the extension of Riese rings, so there is algebra of J inside, there is algebra of I, okay, is integral. Or if you want, module finite. So is integral as a ring extension. So what does this mean? This means that every element of RIT, of this ring satisfies a monic polynomial equation with coefficient in RJT. Reduction were actually first introduced by Notre and Riese about 70 years ago, and they have been, widely studied in multiplicity theory, in equisingularity theory, and for example, in the study of Riese rings, to just name a few. Intuitively, you think about reduction as simplification of the given idea, which carry most of the information about the original idea itself, but in general with fewer generators and a better structure. So obviously, a very important information is how close they are, and this is given by this n. So let me tell you what this is, what this represents. The smallest n for which this happens is called the reduction number and also denoted like this. And it does depend on J. So it's the reduction number of I with respect to J. The reduction number is a crucial invariant in the study of Riese algebra. And as I said, it measures how closely they are related, because what it does is actually bounds the degrees of the generators of RJT as a module of RIT as a module over RJT. So, and clearly, as small as the reduction number and as nice as J is, when we have the best result. And this is exactly what we look for. So since we look for the best J, what does the best J means? It means really that J should be, if you want, the one with less generator, but or you could also say it should be the smallest in terms of inclusion. And in this sense, we define minimal reduction. So minimal reduction are the best J, and they are really minimal with respect to inclusion. And we can talk about minimal reduction. They exist if our ring is a local ring. So we assume now that we are in a local ring from now on, because then minimal reduction indeed exists. Now, an idea of the theorem that I'm talking about is exactly this kind of theorem that, for example, was proved by Vasconcelos. This is a sample theorem of the strategy that I'm trying to outline here. How you use reduction to study this ring. Suppose that J is a complete intersection, so the possible best reduction. And the reduction number is the best possible, so is less than equal than 1. And assume that your ideal is actually Comecoli, and the height, let's say, of the ideal is at least 2. Then there is algebra of I is Comecoli. And the idea is exactly what I already outlined. There is algebra of J is going to be Comecoli because this is a complete intersection, and they're close enough so you can carry off the property. Now, and these are more technical conditions. You need to actually assert that there is algebra of I is Comecoli. You wouldn't need this to say it about the associated ring of that is Comecoli, but for there is algebra, you need it. So the problem with reductions is that reduction, they are not unique. Actually, the picture we can, and also minimal reduction, obviously. Reduction are never unique, but not even minimal reduction are unique. So the situation you can think about is like this. So you think about reduction as this a smallest ideal over which I is integral. And on the other part of the spectrum, you can find its counterpart, which is the integral closure. The integral closure is and this is unique, you see that the difference, the largest ideal integral over I. And again, so this is called the integral closure of I, and it's a very important, idea related to I bigger than I. Obviously, you could define it just using the definition of integrality I gave above, but you can also define component-wise. I mean, in terms of element, you can say that is the set of all x in R that satisfy an equation whose coefficient, a monic equation with coefficient are in largest and largest power of I. So k equals 0, and the AI sits in the I power of I. So this ideal is unique, but J, unfortunately, minimal reduction are not unique. Notice that though integral closure is so connected to reduction, because J is a reduction of I clearly, if and only if the integral closure of J is the same as the integral closure of I. And actually, by a theorem of Rizzo's generalizations, and one of his generalizations was spoke by Chung in this seminar recently, we can check this kind of that J is a reduction just numerically using multiplicity or generalized multiplicity. And now, because reduction, there are infinite many, to remedy to this lack of uniqueness, Reason Sully introduced this object that we'll talk about today, which is the core of an ideal. And this object is the intersection of all reduction. And actually, you can even just intersect on the minimal reduction. Let me call it, because this is going to be an important set, like this, mi, and this is exactly the minimal reduction of I. And remember, I assume that now my ring is local, so I have a lot of minimal reduction. And actually, so let me say something about the core before diving in. So I think the problem with the core is that exactly because it's an intersection of infinitely many ideals, it's very difficult to study. It's very mysterious. It's a sub-ideal of I, which is very difficult to get your handle in. It's very difficult to compute. How is an infinite intersection, but how big it is? It's definitely not a reduction. However, it's obviously contained in I. This is clear. But actually, it's not so small because it shares the same radical as I. So I is contained in the radical of the core. And why is it important to study it? But it encodes uniform property of reductions and also gives information about the structure of the Rees ring. And I'll say more about the motivation. Let me tell you a little bit, just name some people that I've worked on. Definitely the first person I should at least write the name is Rees and Sully, because they introduced the core in 88. And then I should write the name of Unick and Swanson, because they were the one to actually first study the core in 94. And then the next name I should put is the one, of course, of myself and Ulrich, because we did a systematic study of the core in several papers where we put actually the foundation. Then there was work of Erie and Smith, several papers, and Erie with Jarvileto, then work of Unick and Chung, and then myself and Ulrich, and then myself, Ulrich and Vitulli, a lot of work of Watanabe, work of Fuli with myself and Ulrich, and then work of Cumming, work of Wang, work of, Kohlhaas, Bonnie Smith, Morey, Jonathan Montano, Kim, and many, many others. Now I won't mention everybody, but there is a lot of work done after on the core. So let me tell you instead the motivation, as I started telling you before. Why would one want to study the core? So the motivation are as following. First of all, we want to find uniform properties of reductions. And so, for example, if an element lies in all reduction of I, you could ask, how deep does it sit into the ideal? And this is a very important question. In the monomial case, for example, and we'll see that on Friday, the core is strictly connected to the largest monomial ideal, who is contained in every minimal reduction of I, in all reduction of I. So core, for example, came in the proof of Ongeta and then of Unick and Secelenau and Mantero and McCullough when they work on bounds on the Stillman problem, because knowing the core helps you really understanding better the ideal. So the core detects also algebraic properties of the Rees ring, and I hope I will show this more during the talk. And then it appears naturally in Briançon-Skoda theorems. Actually, I would say that Briançon-Skoda theorem is really a theorem on the core, and then is connected to the adjoint, also known as multiplier ideal, and then it plays a role in one of the conjecture of Kamata by work of Edie and Smith. And we'll talk, maybe, I don't know if we have time, but we'll talk about this more later. And then it reads geometric properties of varieties. And in fact, to just give an example of the last point, we can characterize if a set of points in projective space is Cayley-Bacharach in terms of the degree of the shape, actually, of the core. And which core? The core of the maximal ideal of the homogeneous coordinate ring of the set of points. Recall that if you have a finite set of points, let's say S points in Pn, is called Cayley-Bacharach if you consider any subset of S minus 1 points, it has the same Hilbert function. And the point is, with Fourier-Ulrich, we prove that a finite set of points in projective space is Cayley-Bacharach if and only if the core is as simple as possible, if and only if the core is just the smallest as possible, if and only if the core is just the power of the maximal ideal. So to start studying the core and actually tell you what I'm going to look in the core, first I have to define some invariants. So let me tell you what minimal reductions have in common. This is really important because the core is the intersection of them. So this is the first question we should ask when we want to think about the core. Then what's happened? Remember that I have a local ring, and not only, I assume now that the residue field is infinite. Then our ideal I, let's define, because this through the talk, let's call G the height of our ideal, and let's assume it's positive. And I'm going to look at the minimal number of generator of my minimal reduction for every minimal reduction. And this number is actually constant. And we'll denote this number with L. And we'll call it the analytic spread. Since reduction have the same radical as the ideal I, the height of the reduction, the height of I are the same. So by Krull altitude theorem, L then is bigger equal than the height. So it's bigger equal than G. And now it can also be characterized, and that shows Y is independent of the minimal reduction, as the dimension of the special fiber ring of I. And what is the special fiber ring? The special fiber ring is nothing else but the Riesz ring of I. Let me write it as I wrote it throughout the talk, RIT, tensor with the residue field. And why is this true? It's because minimal reduction arises as Nether normalization of this ring. And we know very well that the Nether normalization has the same dimension as the ring itself. And now, since this, you could obtain also the fiber just tensoring the associated graded ring with K, and the dimension of the associated ring is the dimension of the ring, this is less than equal but the dimension of the ring that we denoted by D. And so we have that the analytic spread is bounded between a sandwich between G and D. And now let me state Briançon-Skoda theorem, since I told you that Briançon-Skoda theorem is the theorem where the core appears the first time naturally. And Briançon-Skoda was really, I mean, the first proof is due, the first algebraic proof from Lippmann and Satire. So let me write it as R is a regular local ring. And then what it says, I look at the reduction, actually every minimal reduction. And it says, obviously, a power of I will be contained in the reduction, but it doesn't say that a uniform power of I is contained in the reduction. It says much more. It says that the integral closure of a power of I, the L power, where L is the analytic spread, so in particular the D power, since L is less than equal than D, is always contained in every reduction. So every minimal reduction contains, even the minimal, which are the smallest, contain a large piece of I, because it contains the integral closure of I to the L. So it really puts this integral closure, if you want to, because it's very difficult, it's also an open problem. How do we compute integral closure? It puts this big integral closure inside J. And obviously, since this is inside every J, we can write it in terms of the core. In terms of the core, it just says that this power is in the core of I, since it is in every reduction. That's why I call it a theorem on the core. Actually, we can say more, and this is an improvement of Briançon-Skoda given by Lippmann in 94. We can put here the adjoint, and I'll tell you, I'll define next what the adjoint is, of I to the L inside the core. And this was proven by Lippmann in 94, and that we should think of it really as an improve of Briançon-Skoda theorem, because it puts an even a larger ideal inside the reduction. So let me tell you what the adjoint is. The adjoint, so I'll give you the definition of Lippmann. The adjoint of I is the intersection among all the divisorial valuation. And if you don't remember, the divisorial valuation are just V, which are DVR, essentially of finite type over R. And they are they sit in between R and the quotient field of R. Okay, so you take the intersection among all the divisorial valuation of the ideal I, multiplied by the Jacobian, actually the inverse of the Jacobian of V over R. And if you want, you can also write it as the intersection of I extended to V, okay, and then colon this Jacobian ideal. So again, what is the Jacobian ideal? I won't really define it if you may not say anything if you are not really familiar, but to remind you, if you are familiar, the Jacobian ideal of V over R is simply the zero fitting ideal of the modulo differential of V over R. Okay? And this is the Jacobian ideal. Now, it turns out actually, so first of all, let me tell you why the adjoint is important. The adjoint has been used to prove a lot of uniform bounds. As we saw, Lippmann used it, introduced it to prove the Briançon-Skoda, improvement of Briançon-Skoda, but it's also been used for the containment problem of symbolic power that we talked a lot about, and is related to something that is maybe a little more fashionable, at least in characteristic 0, is called the multiplier ideal. That's what is defined. And in analytic geometry was defined introduced by Nadel and CU and Desmaillet, and in algebraic geometry by Hainaut and Fivek, in connection with vanishing theorem, because the multiplier ideal, it measured the singularity, and deeper or smaller is the multiplier ideal, and worse the singularity is. Obviously, this has a different definition in terms of resolution of singularity, and I don't have time, I don't go in this, but in characteristic 0, they are the same thing. And what turns out is that the adjoint of I, it's actually very easy to say, but to show, but I don't have time now. The adjoint of I is an ideal of R And clearly by the definition, since you do it going to the valuation, is integrally closed. And furthermore, you can see immediately from the definition that I itself, because of this column, is contained in the adjoint. But actually, I is always contained in the integral closure, obviously, of I, which is contained in the adjoint of I bar, obviously, but the adjoint of I bar is equal to the adjoint of I, exactly because of the definition, because it's integrally closed. Because it's integrally closed, it has to be containing, every integrally, it's the largest integral closed ideal, so it has to contain, obviously, a joint of I bar, so they're equal. So this, so you have this inclusion always. And also another way, also that you could have thought about I bar, remember, is also the intersection of IV, where V are divisorial valuation. So that shows immediately that I bar anyways in the adjoint. So the question is, look at this. Let's go back to Lippmann, to Briançon-Skoda, to this, to what we have at the beginning here. You have this inclusion. And the first really open problem about the core is, when is this inclusion inequality? So a way to formulate it is saying, when is the core equal the adjoint of I to the L? Okay, so I can put it back here because this is a very important question about open question. And this is not going to be the case always, because the core, for example, has to be integrally closed to be the adjoint. And this is not the case always. So we would like to know when the core is integrally closed. We would like to know which condition, for example, on the Ries ring, give us this equality. This is actually connected. And again, I don't think I have much time for it, so I won't really talk about it. But this, if I have time, I'll talk about this at the end. But this is connected really to, as I said, to Kawamata conjecture, because to a conjecture of Kawamata about non-vanishing of sections, because it talks about an ample line bundle, and we know that an ample line bundle has, many, a very large power is globally generated. So it has a lot of global section. However, the problem is whether the ample line bundle itself has already a non-trivial global section. So you look at the ring generated, the section ring generated by all this global section, and you ask if he has a generator in degree 1. And this question was actually interpreted by Ian Smith in terms of this equality, and more precisely the quality of the graded core, which is the intersection of homogeneous reduction and the adjoint, the power of the adjoint. But as I said, I won't talk about this much now. I want you to think about it more as a motivation. Let me tell you the goals I would like to achieve in the rest of the lecture, which is a little bit less than half an hour. So the goals that I have for this lecture are to describe general property, and that's what I start, of the core, and then give explicit formulas. Obviously, explicit formulas are extremely important exactly because the core is so mysterious, because there's an infinite intersection. And now, I will also try to explain how the core is related to the Ries ring, and I hope I'll do that. And also when it is integrally closed, and what is the relation with the adjoint. So I would like to achieve this during this talk, if I can, in the end of the talk. Let me first again stress out that my ring is local, and I also assume that it's Kumekoli now, and the residue field is infinite. And then which assumption I have, I'll call them star, these are important assumptions. and that are going to go throughout. So the first assumption is that the ideal I has to have GL. This is just a local property sorry, this is just a property, a condition on the local number of generator of the ideal. That doesn't tell us anything about the number of generator of the ideal globally. So it's very mild and actually can be checked very easily just from the presentation matrix of the ideal. And this tells us that the minimal number of generator of lies at P is less than equal than the dimension of Rp for every P that is in V of I, with the dimension of Rp less than equal than L minus 1. L is the analytic spread, so since L is less than equal than D, this is strictly less than D. So this is important because it does not impose any global restriction on the number of generator. And GL is actually very much needed if you want to say anything about the core. We will come back to this on Friday. It's very difficult to say anything about the core if you don't have GL. The other condition that instead is less restringent, but I want to assume in this case to make my life simple, is a depth condition on the power of I. He asks that the depth of R over J is bigger than equal than the dimension of R of I minus J plus 1, and this for every J between 1 and L minus G. Remember that L is bigger than equal than G. So this could be 0 if the ideal, if L equal G, which means the ideal is equimultiple, in which case is vacuous. And in fact, I have to say that this assumption on the depth, you know, as I said, is not really necessary. I mean, is for some statement it is, but much less usually is needed. What we really need is some residual intersection condition, and these though are quite technical, so I think I prefer to avoid them for this talk, and I just want to give this because they're just easier to write and to state and to understand. And now I want to look at a class of ideal that satisfies them, but first of all, a primary ideal. And primary ideal always satisfy both conditions. And actually, more generally, any ideal that is equimultiple, which means L is equal G, will satisfy this. And then both of them, this will, GL will be vacuous, and also this will be vacuous if L is equal G. And then ideal that are one-dimensional, generically complete intersection. Okay, so complete intersection when you localize at the associated prime, and in general, this actually more in general, the class that satisfy these are every generic complete intersection, generically complete intersection, which is come-coli, doesn't have to be one-dimensional, but has to have L minus G, L equal G plus 1. So you see, this is really the general case for this is L equal G, and the general case for this is L equal G plus 1. But obviously you need more. You need also come-coli and generic complete intersection. Another class of ideal is I, GL, and Lichy. Lichy means in the linkage class of a complete intersection. And more in general, again, I should be strongly come-coli. This was introduced by Unike, and this condition means that all the Koszul homology are come-coli and GL. And examples of such ideal are, for example, perfect ideal of I2 or perfect Gorestan ideal of I3. With GL, they have this property. So now that I tell you that the classes of ideal is quite big that we can look at, let me state the first result actually on the structure of the core. And this is the first theorem that I want to state today, which is joint work with Corso and Ulrich, and says that if I S star, so satisfy star, that's what we assume, then the core of I is a finite intersection of general minimal reduction. So, and actually, so first of all, let me tell you what general means. With general, I means that where you just take L random linear combination, L is the analytic spread of the generator of I. Another way to think of it, you go modulo the maximal ideal, and you choose a point in an open dense set of affine space of dimension L cross N. Okay? So in fact, more is true. And if you take G1, GA, T plus 1, which are general minimal reduction, of I, and if you intersect them, you actually intersect first T and then intersect T plus 1, and you obtain the same thing, so it stabilizes, then this tells you that you already reached the core. So it's very powerful computationally, because it's really our only way to compute the core. Computationally, it's a very good way, because it tells you that you can just keep intersecting general minimal reduction until they stabilizes, and then you have gotten the core. And it's important that the reduction are general. Otherwise, you wouldn't know which reduction to choose to intersect the core. You know, it could be very strange. And then how do you could not do it, and then it wouldn't, you know, it wouldn't be an effective method. But since you can just take general reduction, this is very effective. And this allows us also, not just by the computational point of view is very important, but it also from the theoretical, because it allows us to prove a many theorem. For example, it allows us to prove that the core behaves well under flat maps, like localization or completion. So this is the next thing I want to write about the core. These are really the two properties I want now to focus on for these talks. There is much more we can say, but this is what I want. So the core of I extended to S is the core of I extended to S. So the core localizes, for example. I want to say that this intersection will come up also in next talk, because it's very important, as I said, from the theoretic point of view. It's really a very important tool we have. Now I want to go to the second part of the talk. I don't have much time, so I better go there, which is formulas for the core. So let's talk about formulas. And when we talk about formulas for the core, really the first name that should come to mind is Unique and Swanson. They gave the first formula on the core, and they consider a two-dimensional regular local ring. And they consider the class of ideal they consider were integrally closed. Okay. And what they could prove is that the core of I is I times the second fitting ideal. Remember, in this case, I is just given by Hilbert-Birch matrix. So this fitting ideal is very clear from the presentation matrix. And this is I, and this fitting ideal is nothing else but the adjoint in this case. This was known also by Lippmann. And this is the adjoint of I squared. This is a beautiful theorem. Actually, as beautiful as it can get. It tells you that what I asked before, if the core is the adjoint, and it tells you also that the core is divisible by I, and it tells you that you can write it in this nice shape. And now, furthermore, obviously says that since the core is the adjoint, the core is integrally closed. And there are many properties that obviously come from here, and they point out in their paper, in this beautiful paper. So when you try to generalize this, and you try to go away from regular local ring or from integrally closed ideal, and you want to do it for any ideal, you ask what is really crucial here. And what's really crucial is the reductions, the idea of reduction number. So let me actually give you the definition of reduction number in general. This is, remember, the reduction number usually depends on the reduction. Since we want to look at the core that varies among all reduction, we better look at the reduction number, which is the minimum of all the reduction number of I with respect to j, where j is varied along the minima reduction of I. And this is again an important invariant which was widely studied for when one studies the Ries ring and studies reduction. Okay? And so what could we prove in this general situation? So the next theorem is actually due to Corso, myself, and Ulrich, and that says assume again that I satisfy star. And also R is Goresten, so it's not a regular local ring, but it's Goresten. Then what we can say is that if R is less than equal than L minus G plus 1, so actually is a if and all if, which is very important because it really says that the core reads the reduction number. As I told you at the beginning, it reads information about also the Ries ring and the reductions, because it says if R is less than equal than L minus G plus 1, if and only if the core of I is exactly equal I times J colon I. And furthermore, you can also write it as J times J colon I or as J square colon I. Okay, so let me tell you some things first. First of all, I want this strange number. This is called the expected reduction number. And this was already introduced by in the work of Simis, Ulrich, Vasconcelos in the study of Ries ring. So it was a very well-known number that was known to imply or to actually you could write necessary and sufficient condition for the Ries algebra to become a Colli in terms of this number. That's why it's called the expected reduction number. And
excuse me, Claudia.
yes.
Here J denotes minimal reduction. Any minimal reduction?
This is for every J.
Okay. Thank you. Yeah.
For every minimum reduction, any you want. And in fact, what's happened is that this J colon I is so-called balanced. That was already observed by Ulrich before. And so it does not depend on the reduction, which this is very important in the study of the core. And this corresponds exactly to the fitting here in this theorem. And I also want to notice that this, in the case, this really recover Uniquet-Swanson formula, because by work of Lippmann and Tessier, in this case, the reduction number is the expected one because it's less than equal than 1. So indeed, this recover that case. What we cannot recover is the fact that the core is the joint, and it will not be in general. Now, in this same paper, we actually conjecture a more general theorem shape for the core, even when the reduction number is not the expected one, so it's larger. And we proved it later, and actually a first version of this theorem was proved by Erie and Smith, but in more restricted condition. The ideal was in primary, and by Uniquet and Chung at our same time, but also in more restriction condition. I think they assume equimultiple, L equal G. We assume star. So again, you assume that I as star, so the condition is before, and again, R is Goresten, remember. And furthermore, we assume that the characteristic is either 0 or is large enough. So here we see a condition on the characteristic. Then the core of I has this shape, Jn plus 1 colon In, for every n bigger than equal than the maximum of 0 and R minus L plus G. And this, again, you can do it for every J minimum reduction of I. You obtain this for every J, not just for general, for every, okay? And to this day, almost 15 years later, this is still the most general formula we have for the core. We could ask, is in this case possible to divide the core by I or by J? So to write the case J times J to the N colon I to the N. Remember, colon means you look at all the elements of R that send this power I to the N inside J N plus 1. And this is not possible in general. as it shows by an example of Einzel and Lanz and collaborators. So it's not possible in general to do that. There are some situations in which it is, but not in general. So what is the idea of the proof? I think I want in the last 2 minutes, I want to give the idea of the proof because it will actually lead to, maybe just very, very briefly, it will lead to the next part, which is the corollary and what we know about the core being integrally closed and the core being the adjoint, and also shows more the relation between the core and the Ries ring. You see, first you have to prove this inclusion. And this inclusion is really shows how the core is connected to the canonical module of the Ries ring. We consider the extended Ries ring of I. So this is just R in negative degrees. And this is inside, first of the one of J. Sorry, this is the one of J, the one I consider first. And we consider the Ries ring of I that contains the Ries ring of J. Okay, and this extension is finite and birational, and this is very important. Now, the advantage is that A is known to be Come-Coli, and the canonical module of A is known just by residual intersection theory. And then we can, because this extension is finite and birational, we can express the canonical module of B in terms of the canonical module of A as an hom actually, so the fractional ideal. And this is nothing else but the direct sum. I mean, this is not easy, but I just write down the formula of these columns in the component, and here is the component inside our TT inverse. And now this is very important because if you look at the canonical module in component G, this canonical module obviously is independent of J because it's just the canonical module of the standard Ries ring of I. However, the component degree G, if you just do some calculation, is exactly Jn plus 1 colon I to the n. But this is contained in Jn plus 1 colon J to the n because J is contained in I. But this is equal to J because the associated graded ring of J is Come-Coli for every J, which is a minimal reduction of I. And this doesn't depend on J, so this tells us that this is contained in every J, so it's contained in the core. So this component of the canonical module, which is exactly this column, is contained in the core of I. Now the other inclusion is other, and it requires to go actually quite technical because it requires to go to reduce to analytic spread equal 1 by modding out a suitable residual intersection and then to lift the result again using residual intersection theory. So, but I would like at least to say the result in the case that L is equal G equal 1 because that's very interesting and independent of this situation. Actually, you just need a Come-Coli and any characteristic, and it gives a different formula for the core, and it gives the following formula. The core of I is Jn plus 1 colon, not I to the n, but a strange ideal. You take the sum over fixed minimal reduction again, and you take the sum over J comma Y, which is ideal what you obtain just adding Y to J for every Y in I, and this is true for every n large enough. And this was inspired by work of Unick and Swanson, and actually this ideal is I to the n if the characteristic is 0 or large enough, okay? And that's how we get the formula in our situation, and then we lift it back. So in general, what this tells us, this theorem tells us a lot of things. That's why I want to put the theorem, and also because of the consequence that come from the theorem. It tells us that the core of I is a component of the canonical module. So it tells us the relation between the core and the Ries ring. It tells us that in general, for arbitrary characteristic, the core is always sandwiched between this Jn plus 1 colon In and this other ideal that now I'll just copy paste so I can be a little quicker. But actually, by example, oh, let me move it in the center. Oh, it's not collaborating. Silly. Okay, maybe I would have wrote it, I would take less. In any case, it's always contained in between and is in general not equal. This is for every n bigger than equal than the maximum of 0 and r minus L plus G. And actually, by example provided by Fully and myself and Ulrich, and in arbitrary characteristic, we can prove that neither inclusion is an equality. And even we can even give a counterexample in case of monomial ideal, where either inclusion is not an equality. So then with Fully, let me see if I have time. I have 4 minutes. I would like to at least write some theorem simplified. With Fully, we could look at the case of arbitrary characteristic, and we could prove that if K is an infinite perfect field with mild restriction on the special fiber, let me say here is not this, is much less, but let me say if the special fiber is reduced, then the formula indeed works. So the core of I is what you want, is Jn plus 1 colon In for every minimal reduction J and for every n bigger than equal than R. So you can still write the core with this, the expected formula. And in particular, as a corollary, this gives you that, which is quite important, and this is important also in our study for the Kelly-Bacharach. It tells you that, again, in both cases, you assume star and everything. You are in the same situation. So here you also have star. If I is generated by form of the same degree, obviously the fiber is reduced. So this is a case generated by forms of the same degree in a reduced ring. Then again, this formula is obtained. Once more. So this in arbitrary characteristic. Now I would like for the last, I have maybe only 2 minutes, but let me in the last 2 minutes tell you what is the connection with the adjoint. I really don't have much time, but this is an open problem that I would like people to actually think and work on, because it could lead to important discovery. So this is really something we should try to focus. And so connection with the adjoint. The core has to be integrally closed, and just because, as I said, the core is a component of the canonical module, we immediately have that if you again assume the same thing star and R-Goresten, so the condition of the main theorem, then you have that, and if you assume that R is normal, see they're all connected to property of the Ries ring also. The proj of the Ries ring is R1, satisfy condition R1 of SAR, then the core is indeed integrally closed. So at this point, we should assume at least R1 for the Ries ring if we want to describe when the core is the adjoint. And if R is a regular like a ring, or let's assume now that characteristic is actually 0, and the proj of the Ries ring as rational singularity, then the core of I is actually the adjoint of I to the G. Or if you want, you can even write it I times the adjoint of I to the G minus 1. And the core is also related. So the core of I, you could ask how many ideal have the same core. So you can go from the core to which ideal, to which larger ideal without changing actually the core. And you can go to what's called the first coefficient ideal of Chuperka. the component of degree 1 of the S2ification of B. Remember, B is the extended Ries ring. If you go to the S2ification of B and you look at the first component, you call it often I check. That's the same, in the primary case, the same is 0 and the same is 1 as I, the largest ideal with the same is 0 and the same is 1 of I, then the core of I is the core of I check. So they have the same core. And all this can be proved immediately just using, I mean, the proof is not as, this is actually due to Lippmann, it's not an easy fact, but the, it can be proved using the fact that the core is a component of the canonical module. However, by work of Iri, we should be careful because Iri proved that if you have an equimultiple ideal, which means the analytic spread is G, and the Ries ring is normally come Colli, then the core can be the adjoint even though if the Ries ring has rational singularity. So, so the converse of this in a certain sense. So you can write immediately example where there is algebra is normal, so in particular a 1, so the core is integrally closed, is come Colli but doesn't have rational singularity. Then you have the core is integrally closed but is not adjoint. However, there are instances where actually the core can be proven to be the adjoint just having that the core is integrally closed, just having that the Ries ring has R1. I don't have time to write them, unfortunately, because my time is off, but there is work of Kohlhaas in the case of she was my student, in the case of monomial ideal, and work done more recently by Kastin, myself, and Ulrich that investigate exactly when the core is the adjoint and just relate it with property, or the R1 property, since really if and only if R1. So I want to stop here because I think my time is up. And I talk more on Friday about the core of monomial ideal. Thank you very much for the attention.
Okay, thank you, Claudia. Very interesting talk. We can take questions from audience. You can open your microphone and ask your questions.
So I have a question.
Yes.
So, right, so your theorem, which is the core is under appropriate hypothesis, the core is a finite intersection of reductions.
Yes.
So out of curiosity, if you do not have appropriate hypothesis, are there just nice examples where the core cannot be realized as a set of finite intersections of reductions?
Okay, that's a very, very important question. So we really have a much general conjecture, and we'll talk about this more next, when next time. And as I said, for example, we need GL, and we need some. So let me say this: the theorem that I'll state next time, which is not just about monomial ideal, which I'll talk about next time. Actually, I think it is about monomial ideal only. But in any case, what we think is that the theorem actually with Ulrich and Corso just requires GL and what we call a residually S2 condition. But even without that, we think that is much more general than the core is a finite intersection. That we need just much less. However, it will not be an intersection of general reduction. That we know. So I have example, I show it even next time. So it will be intersection of finite, but where do you find them? That's a problem. Even if it's a finite intersection, if you don't know where to look for them, you are in trouble. You understand? And that's exactly the problem I want to discuss next time. We don't really have an example because how can you do that of when the core is an infinite intersection? I think I can even next time I'll write down, since answering to you completely, which kind of conjecture we have for when we think the core is finite in general. So we still think we need some condition for that, but very, very, very loose condition to just have a finite intersection.
Wonderful. Thank you for the talk. That was very nice.
Okay. Any other questions?
I have a question regarding the core. Do you have some like a bound or exact number for the number of generators of core?
Oh, I mean, there is some work. I don't know the number of the generators, but there is some work about um, uh, the Hilbert coefficients and other. Actually, there is some work even about the number of generators, but not much done about that. No.
Oh, okay.
Yeah, Claudia, you mentioned result of Lippmann, which
Yes.
talks about the core in any regular local ring when the characteristic of residue field is 0.
Yeah, it's really more connected to the joint. What he really proved, and Lippmann, is it proved is the quality of the joint. And he really didn't work on the core, but he proved it's a quality that here, when I said that this formula, where is it? When I said this
At joint
formula
of the
here,
gth power of the ideal.
yeah, the joint, yes, I'll find it immediately. It is somewhere when I put the joint. Here. Connection with the joint.
Yeah.
This one. This actually was proved by Lippmann in his seminal paper on the joint, and it's not an easy thing to prove. No.
So this is not known when the characteristic of K is positive.
Characteristic. Okay, I think it's known in general. This quality. What is not known is this one. I think Lippmann has it. I think Lippmann has this in any characteristic, if I'm correct. Remember, Lippmann introduced a joint in any characteristic, not just in characteristic 0. That's the advantage of the joint respect to the multiplier ideal. The multiplier ideal was only defined in characteristic 0. The joint in general. And now there is a definition of actually multiplier ideal in in every characteristic, even in mixed characteristic done by Schwede and Lynch and Ma, that reconcile all of this together. But the joint that's the beauty of it, is defined in general.
Yeah. So, when the characteristic is positive, the test ideal is replaced. The multiplier ideal is replaced by test ideal in positive characteristic.
Yes.
So I was just wondering in this situation, if the characteristic is positive, whether there is a connection of core with the test ideal.
I think there is still connection, even in positive characteristic, and there is work also of the Japanese school in the positive characteristic. Obviously, as I said, the core, again, is what really is connected to is the joint. So it's really asking what is the connection between the joint and the test ideal.
Yeah.
Remember that the core is really this, at least in this situation, is really connected to this component of the canonical module. That's where the connection comes from.
So this condition that pros RIT has rational singularities, that is satisfied in dimension 2 automatically.
Yeah. And that's the case of, obviously, of Unique and Swanson, for example. But you see, often R1 is enough to actually check that. As I said, the theorem of Kohlhaas shows that if you have a primary ideal monomial, then R1 is enough to say that the core is the joint. So R1 is actually if and only if the core is the joint, and the core is integrally closed. I think actually what's open, even in that case, even for monomial, that's actually a nice open problem, because she proved it only if I has a monomial reduction. So it's still open if you want. This is an open problem to work with for people. You have I a monomial ideal inside the polynomial ring in n variable, and then you could ask, is R1 property of the Ries ring if and only if the core of I is the adjoint of I to the D, and primary ideal, 0-dimensional. Okay, so she proved it, Kohlhaas, but only assuming that the ideal I has a monomial reduction, which we know, a minimal monomial reduction, which we know is not always the case. So, so this is actually open, and I think she did some progress in dimension 2, but in general, it is open.
I see. So polynomial ring in 3 variables, we don't know this result.
No.
Okay.
We believe
other
it's true, but we don't know it. And this actually would say the same as if and only if obviously the core is integrally closed. They will be all equivalent. So it's enough that the core is integrally closed, which has to be the adjoint.
Okay. I don't see any further questions. So Claudia, thank you very much for your
thank you very much.
We will meet on Friday at the same time.
Same time on Friday.